Welcome to this walkthrough of LeetCode problem number 115, distinct subsequences. In this session, we'll explore effective approaches to solve this dynamic programming problem. Whether you're preparing for interviews or honing your skills, this problem will help you deepen your understanding of subsequences and recursive solutions. Let's dive in. The problem asks us to determine how many distinct subsequences of a given string S are equal to another string T. A subsequence is formed by deleting 0 or more characters from the original string without changing the order of the remaining characters. For instance, from the string ABCDE, ACE is a valid subsequence because it preserves the relative order of A, C, and E. However, AEC is not a subsequence because the order of the characters is altered. The task is to compute the number of ways the target string T can be formed as a subsequence of the source string S. The problem guarantees that the result will fit within a 32-bit signed integer, so we don't need to worry about integer overflow. The input consists of two strings, S and T, where lengths can go up to 10,000 characters each. The output is a single integer representing the count of distinct subsequences of S that match T. Let's look at an example to understand this better. Suppose S is rabbit and T is rabbit. The output in this case is 3. Why? Because there are three distinct ways to form rabbit as a subsequence of rabbit. In the first case, we can remove the first B, leaving rabbit. In the second case, we can remove the second B, again leaving rabbit. And in the third case, we remove the third B, which also results in rabbit. All of these are distinct subsequences because they involve different combinations of deletions to achieve the same result. Now, consider another example where S is bag and T is bag. In this case, the output is 5. This is because there are 5 distinct ways to form bag as a subsequence of bag. For example, we can choose the first B, the first A, and the first G to form bag. Alternatively, we could choose the first B, the first A, and the second G. Other combinations include the first B, the second A, and the first G, or the first B, the second A, and the second G. Finally, we could use the second B, the second A, and the second G. Each of these combinations represents a unique way to form bag, and together they add up to 5 distinct subsequences. There are also some key edge cases to consider. First, if the target string T is empty, there is exactly one subsequence of S that matches T, which is the empty subsequence. On the other hand, if S is empty while T is non-empty, it becomes impossible to form T, so the answer is 0. If S and T are identical, there's only one way to form T, which is to use the entire string S. Another edge case occurs when T is longer than S. In this scenario, it's impossible to form T because there aren't enough characters in S, so the answer is 0. Lastly, for large input strings, where both S and T have lengths up to 10,000, it's crucial to ensure the solution is efficient to handle such cases within time limits. When tackling LeetCode problem number 115, distinct subsequences, we have several approaches to consider. The brute force approach is the simplest to understand conceptually. It involves generating all possible subsequences of the string S and checking how many of them match the string T. While straightforward, this method is highly inefficient. The number of possible subsequences grows exponentially with the length of S, making this approach computationally expensive. For example, with 2 raised to the power of the length of S, even moderately sized strings result in an unmanageable number of subsequences to process. Moreover, matching each subsequence to T adds further overhead, leading to exponential time complexity of O2 to the power of n. This approach is not feasible for large inputs, especially when S can be as long as 10 to the power of 4 characters. Due to its inefficiency, we need to explore better alternatives. The recursive approach with memoization is one such option. The recursive approach with memoization improves upon the brute force method by avoiding redundant computations. Here, we use recursion to determine the number of ways to form T from S. At each recursive step, we decide whether to include or exclude the current character of S. If the current characters of S and T match, we have 2 choices: include the character in the subsequence or skip it. If they don't match, we simply skip the character from S. To optimize this process, we use memoization, storing intermediate results for specific indices I and S and J and T. For instance, the number of ways to form the substring t, j from s, I is cached. This reduces redundant calculations, improving time complexity to O, n asterisk m, where n and m are the lengths of s and t. However, this approach still uses significant memory to store the memoization table, which can be a limitation for large inputs. To simplify this further, we turn to dynamic programming with tabulation. The dynamic programming, or tabulation, approach is the most efficient and structured way to solve this problem. Here, we define a DP table, where DP, I, j, represents the number of distinct subsequences of S, 0y, that match T, 0j. The base cases are straightforward. First, there is exactly one way to match an empty T to any prefix of S, which involves deleting all characters. This means DP, I, 0, equals 1 for all I. Conversely, we cannot form a non-empty T from an empty S, so DP, 0, j, equals 0 for all j greater than 0. Finally, when both strings are empty, there is exactly one matching subsequence, the empty string itself, so DP, 0, 0, equals 1. For other cases, if the current characters of S and T match, we have two options: include the character, which adds the result from DP, I1, J1, or skip it, which adds DP, I1, J. This is captured by the formula DP, I, J, equals DP, I1, J1, plus DP, I1, J. If the characters don't match, we can only skip the current character of S, so DP, I, J, equals DP, I1, J. The final result is stored in DP, N, M, where N and M are the lengths of S and T. This method is efficient and avoids redundant recursion. Among the approaches considered, we selected the dynamic programming, or tabulation, strategy for several reasons. First, it is the most efficient in terms of time complexity, achieving O, n asterisk m. Additionally, this approach can be optimized further to reduce space complexity from O, n asterisk m, to O, m, by using a rolling array. Second, it is highly scalable, handling the problem's constraints effectively, even for inputs where S and T have lengths up to 10 to the power of 4. Finally, the tabulation method provides a clear and structured framework for solving the problem, making it easier to debug and implement. While the recursive approach with memoization achieves the same time complexity, it consumes more memory and has added overhead due to recursion. The brute force method, though conceptually simple, is computationally impractical for large inputs. By adopting the tabulation approach and optimizing for space, we ensure our solution is both practical and performant under the given constraints. The problem we are solving is to find the number of distinct subsequences of a string S that equal another string T. A subsequence is formed by deleting some or no characters from S without rearranging the order of the remaining characters. To solve this, we'll use a dynamic programming approach, which allows us to efficiently compute the result by breaking the problem into smaller subproblems and storing intermediate results. First, we define a 2D DP table, DP, I, J, where each cell represents the number of distinct subsequences of the first I characters of S that match the first J characters of T. The table has dimensions, lens plus 1, x, len, t, plus 1, to account for cases where either string is empty. The base cases are straightforward. If T is empty, there is exactly one subsequence of S that matches, so DP, I, 0, equals 1 for all I. Conversely, if S is empty and T is not, it's impossible for T to be a subsequence, so DP, 0, j, equals 0 for all j equals 1. Now that we've defined the table, let's discuss the transition relation that helps us fill it. For each character pair S, I1, and T, J1, we have two cases. If the characters match, meaning S, I1, equals T, J1, we have two options: either include S, I1, in the subsequence, which contributes DP, I1, J1, to the total, or exclude S, I1, which contributes DP, I1, J. Therefore, the value of DP, I, J, in this case is the sum of these two contributions, DP, I1, J1, plus DP, I1, J. On the other hand, if the characters don't match, we can only exclude S, I1, and the value of DP, I, J, is simply DP, I1, J. Using these rules, we iteratively fill the DP table by processing each combination of I and J. Once the table is filled, the final result, which is the number of distinct subsequences of S that equal T, will be stored in DP, lens, len, T. This approach provides several key insights. First, the key to counting subsequences is systematically exploring all combinations of including or excluding characters from S while ensuring we match T. By leveraging dynamic programming, we avoid the exponential time complexity of a brute force solution, reducing the computation to polynomial time by reusing intermediate results. Additionally, certain edge cases arise naturally. For example, if T is empty, the result is always 1, as an empty string is a subsequence of any string. If S is empty but T is not, the result is 0, since a non-empty T cannot be found in an empty S. Similarly, if the length of S is less than the length of T, the result is 0 because T cannot fit in S. From a resource perspective, the DP table requires O, lens * len, T, space, but we can optimize this to O, len, T, by using a rolling array, as only the current and previous rows are needed during computation. The time complexity remains O, lens * len, T, as we process each cell of the table once. To better understand the algorithm, let's walk through an example. Suppose S is bag and T is bag. We start by initializing the DP table. The base cases are set such that DP I 0 equals 1 for all I, because an empty T is a subsequence of any prefix of S, and DP 0 J equals 0 for all J equals 1, since T cannot match an empty S. Then, we iteratively fill the table. For instance, when I equals 1 and J equals 1, we compare S 0 equals B and T 0 equals B. They match, so we calculate DP 1 1 equals DP 0 0 plus DP 0 1, which evaluates to 1 plus 0 equals 1. We continue this process for all other cells, applying the transition rules. After filling the entire table, we find that DP 7 3 equals 5, meaning there are 5 distinct subsequences of S that match T. To optimize this further, we can reduce space complexity by using a rolling 1D array, and we can prune unnecessary computation by immediately returning 0 if len, S, len, T. Here, we start by defining a class called solution and a method number distinct that takes two strings, S and T, as input. The lengths of these strings are stored in M and N, respectively. Next, we address two important edge cases. If the target string T is empty, there is exactly one subsequence of S matching T, which is the empty subsequence, so we return 1. On the other hand, if S is empty and T is non-empty, then no subsequences can match, and we return 0. Following that, we initialize a dynamic programming table DP, where DP, I, J, will represent the number of distinct subsequences of S, I, that match T, J. To handle the base case, we note that an empty target string T, shocked, can always be matched by exactly one subsequence of any prefix of S, the empty subsequence. As such, we set DP, I, 0, to 1 for all I. Now, we move on to filling the DP table using nested loops. For every character in S and T, we determine if the characters match or not, and calculate the value for DP, I, J, accordingly. When the characters at the current positions in S and T match, we have two choices. We can include the current character from S in the subsequence, which contributes DP, I1, J1, or we can exclude it, which contributes DP, I1, J. Thus, we add these two values together to update DP, I, J. If the characters do not match, however, the only option is to exclude the current character from S, so DP, I, J, is simply equal to DP, I1, J. Once we have filled the entire DP table, the bottom right cell, DP, M, N, holds the final answer. This value represents the total number of distinct subsequences of S that match T. Finally, we return this value as the output of the function, completing our implementation. In this implementation, we begin by defining the method number distinct, which takes two strings, S and T, as input. The variables M and N store the lengths of these strings, respectively. Now, we handle some edge cases. If the target string T is empty, there is exactly one subsequence of S that matches T, which is the empty subsequence, so we return 1. On the other hand, if S is empty while T is non-empty, then it's impossible to form any subsequences that match, so we return 0. Next, we initialize a 2D array called DP. Here, DP, I, J, will represent the number of distinct subsequences of the first I characters of S that match the first J characters of T. To handle the base case, we populate the first column of the DP table with 1s, because an empty target string can always be matched by exactly one subsequence of any prefix of s, which is the empty subsequence. With that setup complete, we move on to filling the rest of the DP table. To populate the DP table, we iterate through the characters of s and t using nested loops. For each cell DP, I, j, we check if the current character from s matches the current character from t. If they match, we have two possibilities. We can include this matching character, which contributes the value from DP, I1, J1, or we can exclude it, which contributes the value from DP, I1, J. We sum these two values to get the total number of subsequences. If the characters do not match, the only option is to exclude the current character from S, so the value of DP, I, J, is simply taken from DP, I1, J. After filling the table, the value at DP, M, N, gives us the total number of distinct subsequences of S that match T, and we return this value as the result. To solve this problem, we start with an example where S is bag and T is bag. The first step is to initialize our variables. The length of S, denoted as M, is 7, and the length of T, denoted as N, is 3. We then create a dynamic programming table, or DP table, of size, m+1, x, n+1, and initialize all values to 0. This table will help us track the number of ways subsequences of S match T. For the base case, we note that if T is an empty string, there is exactly one way to form it from any prefix of S, so we set DP, I, 0, to 1 for all I from 0 to M. The initial DP table reflects this, with the first column filled with 1s and the rest set to 0. Now, we start filling the DP table by iterating over I from 1 to M and J from 1 to N. For each cell DP, I, J, we compare the characters S, I1, and T, J1. If they match, we add the values DP, I1, J1, and DP, I1, J. If they do not match, we simply take the value from DP, I1, J. In iteration 1, where I equals 1, we compare S, 0, which is B, with T, 0, also B. Since they match, we calculate DP, 1, 1, as DP, 0, 0, plus DP, 0, 1, which equals 1. Moving to iteration 2, where I equals 2, we first compare S, 1, which is A, with T, 0, which is B. Since they do not match, DP, 2, 1, is set to DP, 1, 1, which is 1. Next, we compare S, 1, with T, 1, which is A. This is a match, so DP, 2, 2, is calculated as DP, 1, 1, plus DP, 1, 2, resulting in 1. By continuing this process for all values of I and J, we gradually fill out the entire DP table. At the end, the completed DP table for this example looks like this: rows filled with values that represent the cumulative number of ways to form subsequences of T from prefixes of S. The value at DP, M, N, which is DP, 7, 3, gives us the total number of distinct subsequences of S that match T. In this case, the result is 5. With this example complete, we now move on to another example, where S is rabbit and T is rabbit. As before, we start by initializing the variables. Here, M is 7, N is 6, and we create a DP table of size, m+1 is x, n+1, initialized to zeros. The base case is the same. For an empty T, DP, I, 0, is set to 1 for all I. The initial DP table for this example is set up with the first column filled with 1s and all other entries set to 0. We then proceed to fill the table by iterating over I from 1 to M and J from 1 to N. For each cell, we compare the characters S, I1, and T, J1. If there's a match, the value of DP, I, J, is calculated by adding DP, I1, J1, and DP, I1, J. If there is no match, we simply copy the value from DP, I1, J. For instance, in the first iteration where I equals 1, we compare S, 0, which is R, with T, 0, also R. Since they match, we calculate DP, 1, 1, as DP, 0, 0, plus DP, 0, 1, which equals 1. The updated DP table reflects this calculation. As we continue filling out the DP table for all values of I and J, we reach the final state of the table, where each value represents the cumulative number of ways subsequences of S match T. For this example, the completed DP table shows that the value at DP, M, N, which is DP, 7, 6, is 3. This means there are 3 distinct subsequences of S that match T. Finally, we consider one more example, where S is ABC and T is D. Once again, we start with the initialization. Here, M is 3, N is 1, and the DP table is created with dimensions, M plus 1, X, N plus 1. The base case remains the same, DP, I, 0, is set to 1 for all I, while all other cells are initialized to 0. In this final example, we fill out the DP table by iterating over all values of I and j. However, since the character T, 0, which is D, does not match any of the characters in S, every cell DP, I, j, remains equal to DP, I1, j. This means that no valid subsequences of S can form T, and the final DP table reflects this, with all values in the second column remaining 0. The result, DP, M, N, which is DP, 3, 1, is 0. This confirms that it is not possible to form T from S in this case, completing our analysis of the examples. To analyze the time complexity of our dynamic programming solution, we start by noting that the approach uses a 2D table DP of size, M plus 1 equals X, N plus 1, where M is the length of the string S and N is the length of the string T. The first step is the initialization of this table, which requires allocating memory for all M plus 1, X, N plus 1 entries. This step takes M*N operations. Next, we handle the base cases by setting all entries in the first column, DP, I, 0, to 1 for I ranging from 0 to M. This step is linear in M, so it takes M time. The most significant part of the time complexity comes from filling the DP table. This involves nested loops iterating through all rows and columns, I from 1 to M, and j from 1 to n. For each cell, we either compute the value as the sum of DP, I1, J1, and DP, I1, J, if the characters match, or copy the value from DP, I1, J, otherwise. Each operation takes constant time, and since there are M*N cells, this step also requires M*N time. Finally, returning the result stored in DP, M, N, is a simple O1 operation. Combining all these steps, the overall time complexity of the algorithm is M*N. Now let's evaluate the space complexity. The main contributor to the space usage is the DP table, which has dimensions M plus 1 equals X, N plus 1. This means it requires M*N space. Beyond the table, the algorithm uses only a constant amount of additional space for variables like M, N, and the loop counters, which together amount to O1. This gives us a total space complexity of M*N for the basic implementation. However, the space usage can be optimized. Since each state DP, I, j, depends only on the values from the current and previous rows, we don't need to store the entire table. Instead, we can use two 1D arrays to keep track of the current and previous rows, reducing the space complexity to n. When considering the best, average, and worst cases, the time and space complexities remain M*N, regardless of the input, because the DP table must always be fully computed to solve the problem. When comparing this dynamic programming solution to a brute force approach, the difference in efficiency becomes clear. The brute force method involves generating all possible subsequences of the string S and then checking which of them match the string T. For a string S of length M, there are 2*M subsequences. Verifying each subsequence against T, which has a length of n, takes n time. This results in a time complexity of 2 to the power of M*N for the brute force approach, which is exponentially worse than the M*N complexity of the dynamic programming solution. To further validate the efficiency of the DP method, we can analyze its big O mathematically. The DP table consists of M plus 1 equals X, N plus 1 states, and each state is computed in constant time. This confirms the time complexity is M*N. For space, the basic implementation scales as M*N due to the table, but optimization reduces it to n if only 2 rows are stored. These improvements make the DP approach significantly more practical and efficient for larger inputs. When working with this problem, there are a few common mistakes to watch out for. First, it's important not to confuse subsequences with subsets. Remember, subsequences must maintain the relative order of characters as they appear in the original string. For example, if S is ABC and T is AC, the subsequence AC is valid because the order of A and C is preserved. Subsets, on the other hand, do not consider order, which makes them fundamentally different. Another mistake is using a naive recursive solution without memoization. This approach might seem straightforward at first, but it repeatedly solves overlapping subproblems, leading to exponential time complexity, or O(2 to the power of n). For large inputs, this will almost certainly result in time limit exceeded errors. Finally, be careful to implement the correct base case in recursive or dynamic programming solutions. If T is empty, the number of subsequences is always 1, because removing all characters from S forms an empty subsequence. Forgetting this can lead to incorrect results in your implementation. Now, let's address a couple more common pitfalls. One is improper initialization of the dynamic programming table. Specifically, failing to initialize the first column to 1 can cause problems. The first column represents the scenario where T is empty, and this should always be considered valid since we can delete all characters in S to match an empty T. Neglecting this step leads to incorrect results. Another frequent issue is ignoring edge cases. For instance, if S is shorter than T, or if one of the strings is empty, your solution might run into invalid memory access or produce incorrect outcomes. These edge cases are critical to handle properly to ensure your solution is both robust and error-free. This problem is also an excellent opportunity to demonstrate your dynamic programming skills, particularly in interviews. At its core, it's about understanding how to model the problem with a 2D DP table or recursive subproblem dependencies. Recognizing patterns is key here, as many sequence alignment problems, like longest common subsequence or edit distance, use similar techniques. You should also be ready to discuss the trade-offs between recursion with memoization and iterative DP. While recursion with memoization can be simpler to implement, it typically uses more memory. Iterative DP, on the other hand, is often more efficient, but requires careful attention to table initialization and indexing. Furthermore, if the constraints allow, you might explore space optimization techniques, such as reducing the DP table to a single row. Lastly, practicing how to clearly explain your approach is crucial. For example, you should be able to articulate what dp(i)j represents, namely, the number of ways to match the first I characters of S to the first j characters of T. Finally, let's connect this problem to related topics and alternative approaches. For example, LeetCode number 392, is subsequence, is a simpler version of this problem where the goal is to determine if T is a subsequence of S with a yes or no answer. Other related problems include number 1143, longest common subsequence, number 583, delete operation for 2 strings, and number 72, edit distance. These problems involve similar sequence alignment techniques and dynamic programming strategies. When considering different approaches, a recursive solution with memoization is often easier to understand and implement, but it comes with the downside of higher memory usage due to the recursion stack and memo table. Iterative dynamic programming, on the other hand, is more efficient but requires a solid grasp of table initialization and indexing. For those looking to optimize further, space-optimized DP can reduce the space complexity to O(n) by keeping track of only the current and previous rows. This approach, however, can be trickier to implement and more prone to errors, especially for those new to dynamic programming. Balancing these trade-offs and choosing the right approach based on the problem constraints is a valuable skill to develop. Great job following along. To recap, we used dynamic programming to solve the distinct subsequences problem efficiently. Remember to practice this approach and similar problems to strengthen your understanding of subsequences and DP. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!